So we're talking about that exchange option. And one of the easy ways we priced weird options when there was an option that was only dependent on one stock was the discounted expected value. So in those cases, we used Monte Carlo. So we generated many possible future stocks using the S naught as our starting stock price, e to the. This is the same thing as our, how we would grow a stock, but we replace the drift rate with the risk-free rate of return because we wanted risk-neutral pricing. So we would generate a future stock, see what the payoff would be, generate another future stock, see what the payoff would be, and then we average the value. So that would give us our average end value, our expected end value for the option, and then just discounted it back for time value of money. So the value of our option was equal to the discounted expected payoff, where we just take the average, that by expected value, I guess I mean over here, the sum of, take like 1,000 different samples, divide by 1,000, that would be our expected value, and then discount it, e to the minus RT, time value of money. And this worked great, right? We did this on parabolas. We could do this on any sort of a payoff. The nice thing about it was we didn't have to do that integral. All right. Could we do the same thing with an exchange option? Right? We just have two stocks. So we could just generate a bunch of, future stock price 1, future stock price 2, see what the payoff is at those two values, do that like 1,000 times and do the exact same setup. Well, yeah, except that if I do it this way, so N is just, N1 and N2 are just, they're random variables that come from a normal distribution, standard deviation of 1, average value of 0, expected value of 0. So could we do that with these two stocks? Yes, except for the stock prices might be correlated. The returns might be correlated, meaning that if stock 1 is, let's say, Ford, and stock 2 is GM, they're both auto companies from American auto companies. So you would think are generally correlated. They would generally go up at the same time and generally go down at the same time. So it's not like N1 and N2 are just independent normal. They're not independent numbers. They should be correlated. If N1 is a positive return, then N2 should be positive. They should be correlated. Or the classic example is you take like a department store, Macy's, and something like Dunkin' Donuts, and they should be negatively correlated, right? People like to spend money. When times are good, you're shopping at a high-end department store, Macy's, so their stock goes up. When times are not so good, you still want to buy a little treat. You're shopping at Dunkin' Donuts. You're buying your wife or your girlfriend, or whatever. You're buying maybe even yourself. You're buying yourself a coffee or a donut instead of shopping at Macy's. So they should be negatively correlated. So our discounted expected value, we could still do that, but we need to generate ends that are correlated. The returns have to be correlated. All right. So this becomes our next task then. So we're all set to go with this discounted expected value. We could totally do this, except we need to know how to calculate. We need to know how to randomly generate normal random variables from normal distributions. Both have an average of 0. Both have a standard deviation of 1, but they're correlated. And the correlation has to be something that we can dial in, that we can choose. All right, so now this becomes our new problem. So here we are with the solution. Generating correlated normally distributed random variables. That's what we're trying to do now. So this is, it's a tool we're going to use, but this is its own like separate little idea. So here's the recipe. We generate two random variables from normal distributions, x1 and x2, standard normal distributions. So the expected value of x1 is 0. The expected value of x2 is 0. And their standard deviations are both 1. We make a third random variable, x3, by making it the weighted average of x1 and x2. So rho, it's rho times x1 and square root of 1 minus rho squared x2. So rho is going to be our target correlation coefficient. That's the correlation that we want for our two random variables that we have at the end. But right now, x3 is just a weighted average, right? Once you pick rho, it's a number times x plus a number times x1 plus a number times x2 is equal to x3. So once we get x3 then, now x3 has, well, what's the expected value of x3? The expected value of x3 is equal to rho times the expected value of x1, rho's a constant, plus, here's another constant, times the expected value of x2. But the expected value of x1 is 0. The expected value of x2 is 0. So the expected value of x3 is 0. So x1, x2, and x3 now all have expected values of 0. How do I know? So now I make the y's. The y ones, so what are the y's? The y's are our random variables that we're making with a given average. The expected value of y1 is going to be mu1. The standard deviation of y1 is going to be sigma 1. And likewise for y2. Mu2 is going to be its expected value, and sigma 2 is going to be its standard deviation. We're going to show later on that y1 and y2 are correlated with rho, but right now let's show that these things are normally distributed, the y's, that the y's are normally distributed with the given expected value. So now let's do this. The expected value of y1 is equal to the expected value, so I'm going to write this out in full instead of just talking and arm waving here. And now that's going to equal to expected value of mu1 plus expected value. So expected value, it doesn't matter, expected value distributes across a plus sign. And now sigma is a constant, so that can come outside the expected value. The expected value of x1 is 0, so this whole thing disappears. Mu is a constant, so the expected value of a constant is a constant. So our expected value of y1 is mu1. Likewise, same argument, your expected value of y2 is mu2. So they have the target expected value. Now I want to show that they have the target variance. So the variance, and I'll just do U1 to start. So the variance, that's going to be, let's just write it like, the variance of y1 is going to equal to the expected value of y1 squared minus the expected value of y1 squared. We already know what the expected value of y1 is. It's mu1. So expected value of y1 squared minus expected values squared. So let's clean this up. Since y1 is equal to, that's equal to y1, y1 squared inside the bracket would be mu squared plus 2 mu sigma x squared x plus sigma squared x squared when I multiply that out. All right, put the squareds on top. All right, so now let's distribute this expected value across these pieces, across these two plus signs, and anything that's a constant is going to come outside the expected value. So that's going to be the expected value of mu1 squared. Actually, since mu is a constant, the expected value of that constant is just that constant. 2 mu1 sigma 1, those are constants, so they can come outside. And here we've got then the expected value of x squared. And I still have this minus mu1 squared. All right, now this mu1 squared cancels this minus mu1 squared. The expected value of x1 is 0, so this whole piece is gone. So the only thing left is sigma 1 squared expected value of x1 squared. And since x1 comes from a standard normal distribution, the expected value of x1 squared is 1. So this whole thing just equals the variance of y1 is sigma 1 squared. So the standard deviation of y1 is sigma 1. So what does this mean? This means that our y1 is normally distributed with our target, an expected value we pick, mu1, and a standard deviation we pick, sigma 1. Now, the same argument we can make for y2. Well, I know that we argued out the expected value for y2, but you might be, how do I know the variance of x3? Right? If I replace all these 1s with 2s, if I'm doing y2, this would be the expected value of x3 squared. And if I make it 1 in that argument, then I can just point at this and go, it's the same thing for y2. So I guess I have to show you what's the variance of x3. It's going to be 1. That's what I want. So the variance is going to be same thing. Expected value of x3 squared minus the expected value. So it's the expected value of x3 squared minus the expected value of x3 squared. The expected value of x3 is 0. We already argued that out. It's a weighted average of 2 zeros. So the variance is just equal to the expected value of x3 squared. All right. Well, that's equal to the expected value of, now I'm squaring this piece, x3. So let's put it in there. Let's square it out. So that's going to be, when I square that out, it's going to be rho squared sigma squared. No. Rho squared x1 squared plus 2 and then times this piece. And finally, plus this piece times this piece, so that's going to be and squaring is just going to get rid of the square root sign. Okay, so we're still taking the expected value. I'm going to do the same thing that I did before. I'm going to distribute this expected value across these two plus signs. And anything that's a constant, like rho squared, is going to come to the outside. So rho squared is going to come to the All right, now what do we got? Well, the expected value of x1 squared, it's from a standard normal distribution. So its standard deviation is 1. Its variance is 1. So expected value of x1 squared is 1. Same deal with expected value of x2 squared is 1. So that's 1. That's 1. Now I have rho squared and minus rho squared. They cancel. Now what's the expected value of x1 and x2? Well, that's the covariance of x1 and x2. These x1 and x2, they're not correlated at all. The covariance is 0. Right? They're just they're independently distributed. So this piece is equal to 0. So the whole deal equals 1. So the variance of x3 is 1. That means that our y2 also works, right? It has the target expected value of mu2, and it has the target standard deviation that we pick as sigma 2. All right. What's left? Well, I'm claiming that the y1 and y2 have a correlation of rho. So far, we haven't correlated these things at all. We've just they're meeting their own target standard deviations with their target expected value and their target standard deviations. I need to show that the y's are correlated. So let's see, I got a list of things here to show that x3 has a mean of 0 and a variance of 1. We did that. Show that y2 has a mean of sigma 2 and a mean of mu 2 and variance of. We did that. Show that y1 and y2 have correlation rho. That's the last thing we got to do. So we want to show I want to know what's the expected value of y1 times y2. Well, that's the expected value of y1 I'll make this a 2 here. And that's now x3. Let's expand this out. Oh, we want to know what's the expected value of these minus their, like the difference from. So I want this So the product of their differences from the mean. So that means that these are gone. And constant and constant, they can come outside. And now I've just got expected value of x1 times x3. And now I'm going to go back in and put in my x3 like this. Okay. If I multiply this x1 through this bracket across this plus sign, that's going to make this x1 squared, and that's going to make this x1 times x2. And now let's take the expected value across this plus sign. That means that constant can come out front. And there's going to be these two sigmas here in front, and there's an expected value of those two pieces. All right, we're almost there, because the expected value of x squared, of x1 squared, that's the variance. This is 1. The expected value of x1 and x2, that's 0. So this whole piece disappears. So we end up getting the covariance of y1 and y2 is equal to sigma 1, sigma 2, the number rho. Oh yeah, that means rho is therefore the correlation is good, right? The correlation is equal to the number is equal to the covariance divided by those two sigmas. So we get our target covariance. The y's have our target covariance. All right, so all of this is proving that our technique works. We were like almost there. Let's go back to what we were doing. We were going to use our discounted expected value. All we had to do was generate stock returns that were correlated. Now we can. So back to a discounted expected value. Our value of our exchange options depended on the value of the two stocks and the time. We're going to make it the discounted expected value of the payoff. I put in the payoff for our exchange option. We're getting Q1 of S1 stocks. We're giving Q2 of S2 stocks. Maximum of that or 0, because we won't exercise the option if it's not beneficial to us. So we can generate two stock prices correlated. So N1, that's going to be standard normal distribution, right? Average of 0, standard deviation of 1, just like we would normally do when we did discounted expected value for one stock. Stock 2, we're going to use N2, but we're going to make it correlated by generating another X1. Make that X1. By making X1 also standard distribution, but making our N2 this weighted average of, with our target correlation, the weighted average of our two standard normal distributions, N1 and X1. So I'm plugging that in for N2. So generate like 1,000 stock, possible future stock values, calculate the payoff, take the average, that's the expected value, average of the payoffs, and discount it. Boom, we can do discounted expected value for basket options, for basket options with two stocks. There are ways to generate correlated random ends for more than two. They're just extensions of the method that we've already got. Right now, we're just concerned with pricing that exchange option.